right, I guess we should just get started. Welcome to CS4510. Class is called Automata. And complexity. So, I guess class started, that means summer is officially over for everyone. Right, so this is being taught summer 2023. I've designed the course hopefully somewhat remotely, so everyone can, people have this or that internship, or they're doing something over there or over here, they want to go home. You guys don't have to come to class, but I would expect you, like if you're on campus or whatever, I would expect you to come to class. Summer is weird in the sense that like in fall and spring, it's like 75 minutes for the class, but I feel like I'm going to be playing with this a lot. It's like 75 minutes for the class, but then in the summer it's 130 minutes. So that's like way too long for anyone to have any kind of attention span, especially every year I think it gets worse, right? So my plan is to split it up into two 60-minute blocks, and then like there's going to be a 10-minute break in between. So there's going to be 4 lectures per week. This first lecture is going to only be on like an introduction, and then the lecture that's going to happen in an hour is going to be like our completion for today. We're going to talk about the just like the opening and the foundations of stuff. Wow, it's really, maybe this won't work. Right, so I don't mind making the course remote because as a trade-off, I get a really nice high-quality set of lectures out, and I can reuse them forever. I taught this course for the first time in summer of 2021, and that was during COVID. It was fully very, very remote. And then I taught it in the spring 2023 in person. So I would hope that these lecture videos could go on and be really nice. To introduce, I guess, the TAs. We have Michael. Yeah, he was a TA in spring. We have Jihao, who has a class right now, can't come. She is a PhD student in crypto. And then we have Akshay, who is also an undergrad in spring. Really, really good TAs, really strong TAs. So in order to succeed in this course, what you're going to have to do, because of the nature of the assignments and everything, is you're going to have to spend a lot of time on the internet and with me, basically. Like I have a really, 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 really fast active Piazza response time. I don't know how to communicate to you how fast I am responding to Piazza, but I will, any ridiculously simple question, I will answer it immediately. Like I think I answered like 1,200 questions in the spring semester, and I had a like average response time of like 5 minutes or something. And I think I answered every single question, right? Or 99% or something. Any ridiculously simple question you have, just feel free to ask immediately. You're also going to have to spend time, like this lecture video is going to be uploaded to YouTube. Maybe you'll have to pause it and unpause it and rewind it, and maybe you can ask me a question about it. You'll also have to spend some time in office hours, and what that is consisting of is you can either come to my office in person, because I'm usually there like 65 hours a week just working on something, or you can come, there's going to be some Zoom calls or something like this that you can call the TAs or me. You know, Michael actually took this course in the summer, and the way like, I have to say this out loud because you're not used to maybe this process, but like you have some question on Piazza, maybe you don't understand it or something, then you just hop in a quick Zoom call, something like this, and then you understand it. There's also, from spring semester, there's 143 pages of lecture notes, and I think they're really good typeset lecture notes, and so basically the notes for this semester are already typeset, and they're already on the internet, and they're already linked there. So they'll be there with the videos. Anything extremal will be commented probably in some way. So here I brought, for example, the first lecture of spring semester in January, and I brought it for me as my own reference today for today's lectures. Grading-wise, what's going to happen? So I wanted to do it very remotely. So this is not a course I really like to do, I think, remote, but compromise means I don't get what I want necessarily. So there's going to be 10 homeworks. Each homework is going to only have 4 problems, and they're due once a week. So then there's going to be 3 exams, and they're going to cover the 4 main units of this course. That's basically it, and everything is take-home. You can do everything online. Fair warning, though, like ChatGPT is really bad at this class. Like some courses, I'll talk quite thoroughly today about the nature of this course, but some courses like ChatGPT, like I heard it could pass the bar exam, right? It seems it can pass like really easy vocab kind of stuff, but this course specifically is unique in the sense that I can't ask you vocab questions. This is a really extremal course in terms of the way you have to think. And ChatGPT straight up fails on every homework problem. We gave our midterm ChatGPT, it made like a 40. We gave someone ChatGPT the final, and it was really obvious, not even from the tone of voice, but just like the straight up, like an answer couldn't be more wrong. In fact, ChatGPT is so wrong, if you could figure out how to code it to flip its answer every time it said no, if you made it output yes, it would be more right than it would be wrong. So maybe you could use ChatGPT in that way, and see what it says, and then understand that it's distinguishably wrong, so it has to be the opposite, right? Something like this. So I'm going to recommend you don't use ChatGPT just because the answers are always wrong. Not even because it's like annoying for me, but it's just genuinely straight up wrong. And yeah, and that'll make sense, I guess, as you see some of the assignments. Oh, also, any questions anytime during anything I'm speaking, feel free to raise your hand, right? About anything. Right, so what is this course about? What is automata and complexity? So there's really two big things. The first one is on computability theory. Computability theory. This is a really beautiful theory of computation. And what does it say? It basically asks, like, what are the fundamental limits of computation? So this is a really, really beautiful theory. This is like extremal. I could lie and say that this is a course on beauty or aesthetics or something like that, the human experience, yada, yada. But it's really not. It's really a computer science course, but I like to think of it as a theory of everything from like a computational lens. So people historically have had all these long, boring philosophical questions, and they've failed to answer them. But suddenly, you ask them through like you can phrase things concretely using computers, and suddenly you can answer them. Maybe not answer them well, but you can at least answer them. This is a really beautiful and fundamental theory, and we're going to probably spend 70% of the course on computability theory. I like computability theory because it makes me feel like a wizard. It's totally made up, by the way. Like everything in this course. The hard part about this course, by the way, is for me at least, is that I'm talking to engineers. I was a math major many years ago, and math majors, theory-oriented people have no problem understanding something being totally useless, having independent interest just because it's cool, you know. So in some sense, all of you guys, what is computer science in general, right? People think maybe it's something we can use to build missile guidance systems or increase the clicks per ad metric or something like this. They go out and their goal is to be, you know, a consultant at a Big Four, and then they can afford groceries, that kind of thing. The computer science is much more than that. It's like a secret third thing. So mathematics is very pure, it's very theoretical. Science is usually thought of to be very empirical. Computer science is like a secret third thing between those two, where we get to employ the scientific method in the way we think about problems, and we don't necessarily deal with empirical data like biology or something like that, right? There's not that many experiments you can do. But we are also very close to mathematics in the sense that we require theoretical thinking. We think about fundamental moving parts like this. For example, like what is an automata in general? When I say the word automata, what do you guys think of? You guys heard the word automata before in any context? Yes?
I heard automaton in the movie Hugo.
I was exactly thinking about the movie Hugo. So it's actually a book too. The book was, of course, better than the movie. You know. So if you guys have seen the movie or the book Hugo, I don't know if the book is called Hugo. I think the movie's called Hugo because the book was something long and boring titled. It's basically like this guy. He lives in a train station, and there's like this. His dad is dead, of course, and then there's like a robot he's like trying to build, and he's like a 19th century British boy, and he's drinking pea soup and doing whatever British people do, and he's like trying to steal parts from the trains and pencil lead or whatever to finish building his dad's robot or whatever, and the robot has all these complicated, like hundreds of moving gears. It's like built by a watchmaker. And he finishes the robot or whatever, and it like draws a picture of a moon, and there's some reference to like the ancient fictional films, like the first films. I forget the name of the director, but there's like a moon with a rocket in its eye and so on. So in that sense, an automaton is like a complicated thing. It does something. So in general, what is computation? Computation is doing things. Write that down. Right? So a highlight of this course, by the way, is that everyone knows, you already know the material in this course, but you just don't realize it necessarily. A lot of this course is just me saying obvious things that you've never heard anyone say out loud, but you know that they're true. Okay? Computing is doing things. Obviously, easy. In the context of this class, an automata is a theoretical model of a computer, is an ideal. We think about this model, this structure of a computer, and then we reason about its power. We'll develop a syntax for us to be able to do that, but that's what an automata fundamentally is. It's a theoretical ideal of a computer. And then we reason about the power of the computer based on what kind of questions it can answer. Right? So like if you think back to I don't know how many of you actually seen the movie Hugo, so I don't know how relevant this is, but like if you could imagine maybe certain kinds of gears and systems can draw certain kinds of pictures or not certain kinds of pictures. There are certain kinds of automata have limitations or a certain power. And we can compare different kinds of automata, relative power, and so on. And why do we care about this? So why do we care? The answer is maybe we don't. And this is, again, talking to engineer-minded people. Who cares, really? I mean, a lot of people think, I take a compilers class, I'm going to go write a compiler. I take a database class, I'm going to go write a query or a database. You're not going to go out there and learn. You're not learning about automata, so you can go out there in the world and build automata. And every year, people at the end of the course, maybe they still don't realize what the point of the automata was. We don't actually care about the automata at all. We care about what can the automata tell us about ourselves, about everything else, about nature, about computation itself. So we use automata as a tool. It's nothing more than that to answer questions that are really hard, that we have no other tools to answer these questions with. That'll make more sense as we talk about what some of these questions are. The automata themselves don't really matter. There are niche applications of them. We'll talk about grammars, and then those are useful in like compilers and programming languages and things. So these things do have application. The application is niche, so people always wonder, where is this applicable? The answer is it's not. So most of the time, you should just disregard I'm going to use this to go build a system. So just disregard that whole philosophy already. And just come in to understanding that we're trying to understand something. We're just building tools to help us ask questions. That's really the whole point of it. This course is also unique because every question, every problem, every class you've ever taken, you've only done one question ever. You've always done one kind of problem repeatedly. You've found a derivative of something. You've turned pseudocode, or whatever. It doesn't matter. Every question you've ever done has been the same question. This is the first class you're going to ever have a second question. It's like you've seen, like a baby, has only seen one thing in its life. It's only seen the color red. Suddenly you see the color blue. It's freaking out, right? The neurons in your brain they don't understand blue. The concept of blue is new to you, right? Same thing with this course. This is the first time you'll ever see a second question. This is the second question you'll ever get, right? This is a very meta class as well. We talk about, it is a theoretical computer science class, but it's really as theoretical as you can get. It's like the theory of theory itself, in some sense. So this is computability theory. It helps us ask questions, and most of those questions are solved in a very dramatic fashion. So that's going to be 70% of the course. The other 30%, 40% will be on complexity theory. And so computability theory, we know how to ask these questions, and we know that they have answers, even if the answers aren't satisfying. In some sense, computability theory is like, if it was like a movie genre, it would be like a drama or something. Complexity theory is we have lots of questions, and we don't know how to answer them. And in that sense, if computability theory is like a drama, complexity theory is like a horror. This is, like I would call this a drama. This is like a horror. This one keeps people up at night. This one has killed many people. You know, many scientists have wasted their careers trying to answer these questions and failed. You know, the first generation of computer scientists who are working on this are now retiring. So, and we still haven't solved any of these questions, basically. We have no answers to like anything here. And these include things you may have heard of from other places, like P is equal to NP. But there's not just that question. That's a pretty famous pop science one. There's like a web of like 1,000 related questions, like P equals P space. We'll talk about what those mean. But there's like an interchangeable, P versus NP is not one question, but really like 1,000 questions all connected through not necessarily bidirectional, but their implications. Like one may imply the other or something like this. So in some sense, we really can't answer anything about complexity theory. We have no idea how to answer these questions. Computability theory, we know how to answer the questions, and that maybe we don't like the answers. Complexity theory, we don't know how to answer the questions. In fact, we have a lot of results that say we don't know how to answer them. Like we're actually farther than solving P versus NP than we were when the question was first announced. Like we have some results or something that say like this kind of proof cannot solve P versus NP. So if there did exist a proof of P versus NP, it couldn't look like this. Something like that, right? We'll talk about that more in depth about what that means. But what that really means is when we have a sequence of results like that, we call that a barrier. So certain classes, entire kinds of proof cannot solve P versus NP. And we know that if a proof solved P versus NP, it couldn't have this kind of specific structure. In that sense, through the several historical barriers we found to this problem, we don't know how to solve it at all, but we know how not to solve it. So ironically, we're farther over the past half century from solving the problem than we are from solving it. It's a very beautiful and very important question, but I'll leave this kind of at the end. We'll get to that later in the semester. First half, at least, we'll spend on computability theory. Right. So any questions before I go on to now we actually start talking about anything important? Yes.
Not really related, but how do they know that certain proofs cannot solve the question? Is that like...
It'll take us a lecture to prove that. That is a hard thing to prove. How do you prove a certain kind of proof can't solve something?
Yeah.
Like, and by certain kinds of proof, I mean loosely you may think of induction, you may think of contradiction, you may think of direct or something like this, right? We know certain kinds of proof can't solve P versus NP. It would take a lecture for us to get into the details, and it's a very beautiful result. You had a question? Yes?
So, if the people who have been doing this for their whole lives don't know what they're doing, then why are we learning about it?
So the question is, if the people who have been doing this their whole lives can't do it, why are we learning about it? Well, so it's like you have to be. Why do anything? Why go to the moon?
Well, like our other classes have like answers.
Yes.
But you're saying there's no answers.
We know we have answers to questions in computability theory in that sense. And you could even say we have answers to every question in computability theory. The questions that are left in computability theory are uninteresting. So a generation of scientists moved on to complexity. We don't know how to solve any of the questions in complexity. They are, as of now, unsolved, and if you win it, you'll get $1 million and so on. I got advice one time from a professor. I used to work in cryptography, by the way. My background is in cryptography, and I told my professor, maybe I should work in complexity. Cryptography is actually founded on complexity. Complexity theorists have given definitions of what is easy, a definition of what makes some problems easy and what makes some problems hard. Cryptographers love that because they want the adversary to have the hard problem and the user to have the easy problem. So cryptography is founded on complexity. I told my professor maybe I should be working in complexity theory because it's like, it's foundational for cryptography. And what he told me is you will die on that hill. So a lot of people have gone into the mines, so to speak, and there's nothing but corpses down there. It's empty. Yes?
Did you define complexity theory? You're just like, what's the problems that are in complexity theory?
Yeah, so it's the study of what makes some problems easy and others hard.
This
That's
refers,
like the question, yes.
this refers to like NP complete problems being referred to as like
Right.
hard or
Yeah. So we'll talk about that in general. The algorithmic approach to complexity theory is a very applied one. You learn about NP completeness as this large class of problems, which all have this nice same property, but there's still unanswered questions about the nature of that class itself. That's just one small part of complexity theory. And in fact, because I spend so much time on it in the algorithms course, I don't spend much time on NP-complete problems themselves in this class. But there are questions that I leave unanswered in algorithms that I say, like, it takes a 4510 level of the treatment of the problem to answer the question itself. And then now you're in this class. So now you take it, now you learn it, right? So all of you should have taken 3510, right? You guys covered NP completeness. You guys know maybe what a reduction is in some level. That's a reduction itself is really just an algorithm. So it's just a transformation itself is an algorithm. So that's really why it's appropriate to teach that in the algorithms course. This is everything else. So this is like, I mentioned in the beginning, like this is the second problem you've ever seen. So in some sense, every class you've done, every problem you solved, you've given an algorithm for something. Like even when you learned a reduction, the reduction itself was just an algorithm. So you just did another algorithm in a funny way. Here, we're not doing any algorithms really. We're like deep mathematical results between things, between classes and problems and so on, right? And it requires a different kind of thinking than an algorithm because sometimes there's no algorithm. Sometimes you can't do things. So sometimes coming at it the direct way is not the best way. So what's going to happen, and this happens for everyone, is the class is going to seem really hard, but then one day you'll wake up and it's going to click. And then every single problem is going to be easy. So every homework problem is designed to be, it's going to be, you should have no idea what the question is asking, maybe. And then once you understand what the question is asking, the actual answer is going to be like one sentence. So the question, understanding what the question is asking is really hard, but then the answer is really easy. So that's really what's tested in those questions. That might seem extreme and hard, but if it clicks for you, and the faster it clicks for you, the course becomes a breeze. It becomes really easy. So you'll have to massage your one-question brain to answer two questions, kind of thing. Okay, so first we need to answer these really hard, bad questions. So let's develop a syntax and a set of tools to allow us to answer this. So again, this is recorded. It should be posted on YouTube later tonight, hopefully. Any more questions about the nature of this class before I go on? Oh, actually, two more quick things. The book I suggest you read is The Theory of Computation by Michael Sipser. I have all 3 editions. I actually own 15 copies of this book. I have a rare preliminary edition and the international edition, this instructor solution manual, and I have like 9 copies of this book. I remember I lent Michael a copy, and I was like, wow, now I don't have the trio of books. But I was like, wait, I can just buy more. So I've inflated the price of the first edition hard copy on eBay because I keep buying. Supply goes down, price goes up, right? So now the hard copy is no longer $3 on eBay. It's like $15. Really sorry for that. I recommend you pick up a copy though. When I was a student learning this, I didn't understand the book at all. I didn't understand. I understood the material, but I didn't understand the point of the book. I didn't understand. Sipser makes all these very specific decisions, And I didn't understand why they were good decisions. But now that I've taught the course, I understand that every decision he's made from like a pedagogical standpoint is a good decision. Like, I really recommend that you pick up the book and then you just start reading it like you would read a bedtime story, and stop reading it when you're done, like when you get stuck. And in that sense, the book really reads itself to you. And a lot of textbooks are hard. They're full of notation and proofs and so on. This is really, really welcoming as a book. And I did have it as a book when I was undergrad, but I wish I had more respect for it. Yes?
Do you lend out any of your 15 copies? Or?
Yes. You can borrow one if you want.
Oh, thank
Like
you.
2 people didn't return it in spring, so that's fine. So I'll just buy more. So yeah, but the PDF, of course, is online and whatever. I highly recommend you pick it up and read it. Just read it cover to cover. Yeah.
So what edition do you recommend?
The great question, because they're all the same. The 3rd edition is the newest, but it's expensive. The only difference between the 3rd edition and the 1st and 2nd edition is the 2nd edition fixed typos in the 1st edition, and the 3rd edition has a section on deterministic context-free grammars, which we don't even know what that means yet, but we don't care in this class about that. That's important for like programming language people or something. It's not important. I don't care personally, so I'm not going to teach it, right? What's cool is I get to teach what I care about, right? So, right. So I guess one more quick comment about the course is this is really my favorite course because, not just because none of it is applied, but because it's about the great ideas. So like the, every once in a while, someone comes along and they have a great foundational idea, like monumental, like Einstein's theory of gravity or whatever. I don't know if that's right, but something like this happens. It's like people come up with something phenomenal, and it's just such an important idea. It has to be taught. Like you have to learn it. We'll talk about what some of these great ideas are. We don't know what they are yet, but they're really foundational, fascinating, important results that were like so influential, not just for computer science, but for all of science, that I like to teach this course in that perspective. Like, it really hit the highlights of everything. The point of this course also is like a graduation capstone. It's really like a finale to your CS degree. It's really, you get to learn why computer science deserves to be called a science. So, yes?
Is this everybody in the class?
No, there's like 23 registered right now, but it's fully remote. And some people are like, they got an internship in this. If you're around in person, it would be great if you can come to class so I'm not lecturing to an empty room, even though I know like 3:30 p.m. summer, it's like, I don't want to come even because it's hot and it's Atlanta. But you should, if you can, come so the room's not totally empty. Yeah. Any more questions before no more stalling before I get to start talking about some math. Awesome. Okay. So first we have to ask really hard questions. We need a way to answer those really hard questions. So what we're going to do is we're going to talk about, we're going to define sigma to be a set, a finite set of symbols or characters or glyphs or whatever, right? So I don't even need to define what those are because maybe you have an intuitive definition of what those mean. Yes?
It's a finite set, so it isn't like a set of sets, right? It's just
No.
a set of the symbols.
Yes. So for example, the 2 most common ones we'll be using are going to be like the set containing the symbol A and the set containing the symbol B. We may also be using the binary alphabet. We could even use the alphabet containing a single symbol. We can use the alphabet containing the English alphabet, Z, capital A, Z, something like this, right? Those are all alphabets. So this is the definition of an alphabet. So an alphabet, finite set of symbols. Everyone knows what an alphabet is intuitively because you speak a language and that language has an alphabet. So every word in English is built atomically of some fixed set of symbols, right? So that one's pretty obvious. We usually fix the alphabet and we don't really care too much about it, but it exists. You will normally use these two. Most problems that we want to study are independent of the alphabet. Like, it doesn't matter what letters you use. So given that, let's say sigma is AB. What is sigma squared?
ABAB.
ABAB. Well,
Wait, is it like A,
yes.
B, B?
Yes. So this is going to be the Cartesian product. You guys remember, this is a discrete math course. You're going to have to remember all these little things. This is just Cartesian product of two sets. Now, you're supposed to use like the comma and the parentheses when you talk about a Cartesian product of elements. But we're just going to disregard that because we're lazy. And this is going to be AA, AB, BA, BB. Okay? So there's another name for that set, intuitively. You guys, what would you, if you were to describe that set to a person, what would you say?
The set of two-letter combinations.
Yes. What is a two-letter combination, though?
String.
String. So this is, again, everyone knows the answer. You just haven't heard someone say it out loud because it might sound too ridiculous. This is a set of strings of length 2. Okay. What is sigma to the n?
Would it just be like a set of strings of like that?
Yes. Okay, awesome. What is sigma to the 0?
Is the null operator? Or the null character?
The null what?
I forget it.
The empty string. This is the set containing this. So following our generalization. By the way, math, there's only 3 numbers. There's 0, 1, and n. That's all the numbers we care about, right? So following that logic, if we just replace n with 0 here, we get the set of strings of length n, 0. So how many strings of length 0 are there? There's 1 string of length 0 uniquely, right, in a string. So what we're going to do is call this epsilon, where epsilon is equal to that. There's 1 string of length 0. It's called epsilon. Yes?
Epsilon doesn't matter, right? It's just like something that
Yes.
is arbitrarily.
We have to, language is an agreement we all have, so let's agree that this symbol means the empty string. Call it the empty string. You could, other books actually used a little lambda, but this is a,
It seemed like the one with like a circle with like a cross through it.
that is very different, actually. That is not the empty string. We'll learn the distinction between that. This is the empty set.
Oh,
The empty set is a set containing nothing. The empty string is a string with no length, right? The difference here is that this is like an array with no elements. This is like a string with no symbols, no length. So like this, there's a type error here that's important later on. This is like an array that contains no elements, right? So it has type of array or set, right? This is a string. This is a type of a string. So here, this is a set containing 1 element, the string with no length. So there's a little bit of play there. This set has 1 element in it. Following this, by the way, we can work backwards and define the alphabet. Instead of defining things from the alphabet, we can just define the alphabet to be the strings of length 1, right? These are strings. Everyone knows what strings are. We're just going to use strings to talk about the problems. I should also say this out loud at least once. Every string or word, by the way, sometimes they're called words, has finite length. If we were to develop a theory on infinite strings, it would be very different. And it's very, very, we don't know how bad that is yet. We'll learn later on, like midway through the course, why we can't do that. But for now, it should be obvious that every string you've ever seen is finite. But someone always asks, what can the strings be infinitely long? No, strings are finite, right? Any questions so far on the stringology part? Yes.
So the set of strings of length 2, that's over the alphabet of size 2.
Yes.
Right, because it's obviously not all strings. of length.
Yes.
Right.
Yes. So the alphabet is fixed,
Right.
and then we start doing all our problems.
Right.
So here we fix the alphabet to be AB. Right, by the way, what is the size, by the way, of sigma to the n?
Is it just n?
The size of sigma to the n.
Okay, wait,
2 to the n.
2 to the n.
Yeah.
In general, though, it's going to be the size of the alphabet to the n.
Right.
So because it's 2 here. So this is actually sigma to the n, right? Because it's 2. But we don't really care about alphabets bigger than 2. There are some very small things that are specific when the alphabet is size 1. Yeah. But most of the time, we don't care between 2 or 3 or whatever. Like a computer, everything the computer does is zeros and ones anyway. Yet somehow ASCII is like what, base 58, right? There's this the ASCII alphabet is like 58 characters, if I remember. Each ASCII character is written with just a byte, right? I'm thinking I remember this. So in some sense, it's back to zeros and ones anyway. We're talking about computation, so we really care about the zeros and ones. Sometimes zeros and ones can get confusing, so I like to use A's and B's quite occasionally. Real quick though, and following this notation, we can do like AB to the n. Well, let's fix it. Let's say AB to the 3, C. We'll say D, C, something like that. This is just a shorthand we use for string notation. This is what? This is just 3 copies of this string. So this is going to be D, A, B, A, B, A, B, C. And then if I did like D, A, B, A cubed, B cubed, C, this would be like D, A, B, 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 C, right? You've probably never seen this notation before, but it's probably obvious, right? If you have variables. Again, the difference between a word and a set is that the elements in a word are ordered. The order matters in a string. This perhaps should be clear. You're just making copies of whatever in there, right? Okay, so that's the stringology part. So why do we care about I guess strings in general? So a decision problem is any yes or no question. So there are many questions you can ask. You might remember from 3510 something about like search versus decision. A search problem is one that has to output the answer. Like actually tell me what the answer is. A decision problem just has to say yes or no. So sometimes the decision problem is easier. You can just say if it exists or not. Sometimes that makes it easier. But this simplifies a lot of the theory for us because we just have to answer like a Boolean, basically, rather than something very complicated. You can also think of a decision problem like a partition of all strings into the good and the bad. So I forgot one more important part of the stringology is that we define this star operator to be the union of I equals 0 to infinity of sigma to the I. So each sigma I is what?
Is that just like the strings of length I?
Yes. Now we're taking a union for all I. So what is sigma star? This is called sigma star.
Would that just be like strings of any length?
Yes. So what is this? What is the set of strings of any length?
Entire language.
Yeah. So like all strings. This is just all strings. So whenever you see somebody refer to sigma star in any context, sigma star is all strings. Every string has a length. So every string is going to be in some sigma I. So the union of all sigma I is going to be all strings. Should be clear. I maybe don't need to prove it. Yes?
Well, so the only thing on that is you mentioned a moment ago that infinite strings doesn't exist. So how would this be handled on that end, since it does go to infinity?
Ah, but each set itself is finite. We have an infinite
Okay.
union of each of finite sets. So there's a difference, and we'll talk about a big point. A big point of this class is the theory of infinity itself. There is a difference between a limit to infinity and infinity. Infinity is undefined, but a limit is always defined. And a limit is a process. It turns out these are very different. I wouldn't fault you, though, for thinking that, because everyone thinks this. I thought that, too. Yes?
Does that include epsilon?
Yeah, because we started 0. So it's actually sigma 0, union sigma 1, union sigma 2, union, right? So every string ever lands in some equivalence class. It lands. These partition the whole set sigma star in some by length. Every string has a length, so every string is in one of them. So it covers all strings. Yeah. So you can think of a decision problem like a partition of sigma star. So sigma star is split into the good and into the bad. That's what a decision problem is, necessarily. So let me give you some examples of what we mean. So a language is a set of strings. We usually use L to denote the language, and it is just a selection of the strings. So L is a language. L complement is also a language. It's just going to be the opposite of the set of strings. So L is the good strings. The things that are good, quote unquote, are going to be in L. Things that are bad, quote unquote, are going to be not in L, necessarily, right? Yes?
So good is just anything that satisfies the decision problem?
Yes.
And bad is whatever it doesn't satisfy?
Yes.
Okay.
So let me just give you some examples. We'll call it L1. W is a word. W is in sigma star. And we're going to say W begins with an A. This is a definition of a language. Every word either begins with an A or doesn't begin with an A, right? There's no way a word can both begin and not begin with an A at the same time. The first symbol is either an A or not an A, right? This is the set of strings which start with an A. So, for example, it contains what? Let's see. Yeah.
Just to confirm, the empty string doesn't begin with an A, right?
Well, I was about to ask that.
Oh, okay.
Does the empty string begin with an A? No. Why? Doesn't begin with an A. So it's kind of obvious. But A is in A, AB, AA, AAA, ABA. These are all in L1, right? Maybe if I asked you, I gave you a language, I asked you to list a couple elements. I won't ask that, but you should be able to do that. You can convince yourself you understand this fully. Right. Let me give you some more definitions of languages. So what about L2? W is in sigma star. And I'm using this notation. The number of A's in W is even. The number of A's in W is even. So number A's of W's. That's what that function means. Is the empty string in this language?
Yeah.
Why?
0 is even.
There you go, 0 is even. By the way, in this class, and I will talk obsessively about why this is true, 0 is a natural number. Other classes, that's not true. This class, it is true. Okay? 0 is natural. 0 is not only a natural number, 0 is the only natural number. 0 is the most natural number. So 0 is a natural number. as we said, the empty string is in L2. What else is in L2? Anything with an even number of A's, right? So like AA. And we don't care about the number of B's at all. So it could be like B, B, B. A would not be in there. But then like B, 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 A, B, A would be in there because there's two A's. 2 is even, so we just say this is in L2, right? We got that definition down, just giving some examples. These examples will come back to haunt us in a little bit. L3, here's one. A to the n is even. So what is this? This is using our notation we just introduced, which is why I'm defining this as an example. It's the strings that only contain A, and then the length of the string itself is even. So does this contain the empty string?
Yeah.
Why?
Because 0 is even.
Yes.
Like you just said.
Just to work it out, A to the 0 would be what?
It would just be the empty
Ah.
right?
Yeah, well, so we have to read back into the notation a little bit. 1 is a number, this is a string. So we want, when we read this literally, we want 0 copies of A. What is 0 copies of something? It's going to be the empty string, right? So this is going to be in L3, right? So A would be in there, A would be in there, and so on. Those would be some good examples of ones that are in there. And then I'll give you 2 more, and then we're almost to our time for a break. So L4 is going to be L4 is going to be generic words again, but then the number of A's of W is congruent to 3 or 4 mod 7. That one's a little harder to list some of the strings in there, but I believe you could do that. Is the empty string in this language? The empty string contains no A's, so mod 7, 0 is 0. So it's just not, that's not 3 or 4. That's true. Okay, that one's a little, we'll talk about all these languages, but that one's like a little harder. Finally, we have like L5. W is a string, and int W here is the Python integer function. And here, instead of A's and B's, we're going to use zeros and ones. Int W is prime. So, like, here sigma is going to be 0, 1. Usually it's clear from the context what I'm talking about, right? Some strings in this one, it's not even clear, first of all, what is the integer. If you call the integer Python, the int function on the empty string, what happens? Does it return 0? Yes.
What does it say for L4 for the condition?
The number of A's and W is congruent to 3 or 4 mod 7. Yes.
What's the int function in Python?
It takes a literal string and it converts it to a number. Yeah, and it returns an integer type. So it's a casting function. In fact, if you're doing binary strings, you have to put a 2 there. Right? Like if you okay, first off, this is a number, or is it? That's not a number. Those are symbols I wrote on the board. Okay? Use the marker with the ink. And those are just that's not a number, okay? That's an ideal. That's an idea. Okay? Numbers aren't real. All right? You should know this. Maybe again, you know this, but maybe no one said it out loud to you. Numbers aren't real. You can't have you cannot have 3. 3 is not a real thing. You can have 3 bananas, but you cannot have a 3. We invented numbers as an ideal because they tell us things about the world in an interchangeable way. Like you can do, if you have 3 bananas and you have 2 bananas, combined you now have 5 bananas. But the idea of addition, of adding these groups of bananas together, has nothing to do with the bananas itself. It's independent of the bananas. You could have done it for 3 hats and 2 hats, and now you have 5 hats, right? So it actually doesn't matter the way we represent the objects when we were talking about them. The ideas we're trying to study are independent of the way we represent them. 17 is written this way in base 10. I could have written it in base 2, though. How would I write that in base 2? Well, it's going to be 16 plus 1, so that's going to be 1, 2, 4, 8, 16. I think that's 16 in base 2, right? These two represent the same idea. Or I can even written in base 17, right, with the 1. So these two numbers are both prime, and they're written differently, though. Oh, I could have written this also. This is also 17, right? So the idea, we're trying to study problems. It doesn't really matter how we represent them, but we need to represent them in some way. That's the whole point of the strings. Yes?
Python int function.
We have to talk about strings.
Oh, okay.
So strings and numbers are different. We just need to talk about the number. We're talking about a number property. Primality is a number property. A number is prime, a string is not prime. So cast that string to a number, and now we can talk about the number. Yeah.
Okay.
So over for L3, the set builder notation doesn't use sigma. So is L3 the same for any sigma?
Let's suppose it'll be more clear when you get into the things. Here, let's just say it's A. It could have been A, just A by itself, by the way. That would have worked fine. But let's suppose, because we'll do this as a problem later, let's suppose it's just there's a B. But if there is a B, any string that contains a B is not an L3. Right. So these are some examples of languages. What do we care? We don't care about languages themselves. We care about solving problems. So if M is any kind of computer, we may run M on a word, W. It may accept or reject the word. So again, we'll talk about different kinds of computers as well. But M is a computer. We give it a word. It accepts or rejects. It says yes or no. It has 2 lights, red and green or whatever, on and off. It returns a Boolean. Somehow it does this. So we care about the kinds of problems that machines can solve. And we formulate that using languages. So we say that M decides language L if M on input W, so you run M on W, accepts this word if and only if the word was in the language. And we say that M on W rejects if and only if W was not in the language. So basically, M correctly decides language L if M accepts W when W is in the language, and M rejects W when W is not in the language. So the good M somehow, and it'll make more sense when we do maybe some concrete examples of things, but M is going to be some kind of computer, some kind of architecture or something. It's going to be able to solve certain problems. So for example, consider L5. L5 is a language about primality, right? If there existed a machine to decide L5, then we know that that kind of machine can determine primality of numbers. The problem of primality itself is within the conceptualization of that machine. That machine knows how to test primality, right? If the machine itself, you can think of it like an algorithm. If there exists an algorithm, a fixed certain kind of algorithm to decide this language, then the machine can decide the language, right? Similar for all of these kinds of things. Different kinds of machines can and can't do different things. So this is just a definition. After, in the next half, the lecture will go through and actually build some machines and talk about some theoretical computers. Right? I think I'll go ahead and, any questions before we take our 10-minute break on this half? Because the next half is going to be slightly different.
Awesome.